Hello, I'm so glad you've joined me for this next video in our series. As you must know by now, this is the Essential Skills for Physical Science series, focusing particularly on paper 1, the physics paper. We trust that this series will give you the skills you need, not just to do well in your exam, but to prepare you for a life in the sciences. I'm Dr. Derek Fish. I've been director of Unizulu Science Centre at the University of Zululand for the past 30 years. This is part 6.3. We're still focusing on equations, and in particular equations dealing with projectile motion. You'll find this on page 48 in your book, and we'll also be looking at exam questions which come from pages 14 to 16. So projectile motion is based on the fact that what goes up must come down. Let me throw it a little bit lower so we can see that the moment this ball leaves my hand, the accelerating force provided by my hand stops. It leaves with a fixed upward velocity. And as it goes up, the effect of gravity slowing it down, slows it and slows it and slows it until at the top that velocity is 0. Then the velocity changes direction and it starts accelerating in the other direction until it returns to my hand. Now it's the same if I have two balls. If I'm trying to learn to juggle and I'm throwing them around like this, they follow exactly the same rules. And in fact, what we need to know is that the time taken for one ball to go from the bottom to the top is the same as the time it takes to fall again. So while one ball is going up, let's get the other ball ready. And then when the first ball's at the top of its rise, I throw the second ball and it goes up while the first ball is going down. So with a little bit of practice and with 3 tennis balls, I can learn to juggle. Now, if we're going to juggle these projectile motion equations correctly, let's start right at the beginning. So before we go to page 48, turn to page 3. You'll see the page number in your bottom right-hand corner, right at the front of your booklets. And let's just check where we are on the contents page. So we're looking at the equations section. And we will also look a little bit at the motion graph section, which was covered in video number 2. To expand the equation section on page 48, it's just a single page, and we're looking at the equations that deal with projectile motion. This is always covered in question 3 in the matric paper, and also some of the work on graphs of motion comes up in question 3. A comment from the examiner: learners still cannot work with scientific equations or formulae. So let's make sure that we get the examiner to write something different next year. On page 4, looking at the curriculum, of course, this comes up under the mechanics section. And vertical projectile motion in one dimension, that means just up and down, represented in words, diagrams, equations, and graphs, is taught at the beginning of grade 12. But of course, you still need to remember your grade 10 motion in one dimension, your graphs of motion, and so on. Question 3 in the exam is usually a medium length question. Over the last 3 papers, it's averaged 15 marks and obviously falls under the mechanics section, which is the largest part of the exam. Now, over the last 3 years, you can see the questions that have come up. The last 2 years have had quite a lot to do with graphs, and the November 2020 paper was exclusively about a graph for a bouncing ball. The previous 2 years were objects that were thrown up and went up into the air and down again, starting from a certain height above the ground. We will cover these 3 questions very carefully at the end of this video. Looking at skills, what skills will you need for this section? Well, conversion of units and changing the subject of a formula, especially that comes up a lot in this equation section. You'll need to know about constants in equations, but mostly small g, the acceleration of gravity, which is 9.8 meters per second squared. But analyzing information in a graph is very important. And as we'll see, the November 2020 question was based entirely on analyzing the information in a graph. So please, if you haven't done so already, also look back at video number 2 on graphs of motion. These skills are so important. And again, as the examiner noted, a severe lack of skills is evident when marking. Mathematical, conceptual understanding, and integration of topics, also free body diagrams, graphs, and equations. Those last two are going to come up a lot in question 3. Let me give you another reason why we take a skills focus and don't just give you the answers. If you just want the answers to previous exam papers, just refer to the memos. And we have given you the marking memoranda in the teacher's pack. But the memos for question 3 can be quite confusing. Let me just show you an example. So here's the marking memo for the November 29 question 3. The 3.1, the recall question, you'll see it's very simple. There's just one answer for 2 marks. 3.2 was only worth a few marks, but just look at all the different ways it can be answered. Option 1, option 2, option 3, going over, option 4, option 5, option 6, option 7, and even option 8. All that just for 4 marks. Now, this is my dilemma. Which of those options do I present to you? So rather than going through all of them or focusing on a particular one, I want to focus on the skills that are involved in finding the correct answer. Any of these answers is fine. It'll be marked correct, but you must find the one that best suits you. Again, question 3.3 for 2 marks, simple memorandum. But question 3.4, the longer question, was for 6 marks. And again, look how the memorandum goes on. Option 1, option 2, option 3, option 4, option 5, option 6, and option 7. So it's quite bewildering that there are so many different ways to answer it. It's useless for you to try to follow all of these ways. Choose one which works for you, and with each one, I will suggest what I think is the simplest way to answer these in terms of the equations of motion. But it's really important that you focus on the skills and on understanding and not just copying the correct answer off the memo. Now, before we get to the equations, which is what the section is all about, let's have a look at some basic theory about projectile motion. But may I stress again that this is not a content-based series. We're just sharpening the skills around the equations. So it's very important to consult your teacher, your notes, and your textbooks. Now, many things that fly through the air exhibit projectile motion, like this person being shot out of a cannon. They travel up and down, and in this case, they also travel forwards. Now, for matric, you only need to understand one-dimensional projectile motion, which is just straight up and down. It's much simpler, but of course, in real life, things normally travel forwards as well. If you play basketball and you throw the basketball through the air, again, it's a perfect example of projectile motion. Viewed from the side, you can see the basketball is thrown upwards and forwards. It travels up to the top of its rise, and then gravity makes its velocity negative. It travels down, and if you've calculated correctly, into the hoop. And these crazy people actually allow themselves to be shot out of cannons because they know that the equations for projectile motion are so good that they will land in their safety net or on their safety mat every time. So you can imagine these people really trust science and really trust these equations. Now, we haven't always known how to calculate projectile motion correctly. And here's an old wood carving. And this is how people used to believe a cannonball traveled about 300 years ago. They believed it went up in a straight line. And as long as it had what they called impetus, gravity had no effect on it at all. And when it ran out of impetus at point F, then it would drop like a stone under the influence of gravity. Now, of course, that is not the case. And here are some more illustrations. This one's a little bit better because at least it's curved, but you can see the beginning and end are straight lines, which is not true. This actually comes from a textbook showing you how to calculate angles and to work out how to hit your enemy camp. I wonder if they ever did, because of course this drawing is completely wrong. And one only has to look at a spout of water from a water fountain to see that it travels in a perfect parabola. And from the moment it leaves the water fountain, gravity starts acting on it and pulling it down. So it travels in this parabolic trajectory, just like the shape of the parabola that you learn about in mathematics. Now, a good way for us to look at projectile motion is to use one of these great PHET simulations again. It's simply called projectile motion. Teachers, it is in your pack, so please take some time to play around with it and learn some more about projectile motion. So here is the PHET simulation on projectile motion. We have a cannon here, and if I fire the cannon, it shoots an object which travels in projectile motion. Now I can shoot it horizontally, I can point the cannon up, and I can shoot it vertically, and I can point the cannon down, and I can even shoot it in a downward sense. But I want you to know that all of these are examples of projectile motion. It doesn't matter in what direction the object is projected initially, but it's under the influence of gravity in all three cases. Now, what's useful is that I can take this cannon and bring it down, bring it all the way down, so the projectile is fired from a height of 0 meters from ground level. And then we can look, for example, if we shoot an object at 45 degrees. Now you'll see also you can change the type of object which you have here. So at the moment it's a pumpkin, we can change it into a cannonball or a person or a piano. You can add air resistance, but you don't have this in matrics, so I prefer to leave that out. And then you can add various different vectors, the velocity vectors or the acceleration vectors. Now, what's important to note is that at school, you don't have to do this two-dimensional projectile motion where the object has a height and it also has a range. And you can see if I put this on, at that point, it measures two things. It measures the time to reach there, the range, which is the horizontal distance to the right of the cannon, and the height, which is the vertical distance above the cannon. At the end, when it lands, obviously the height is 0, the range is 23. Now, in matric, your cannon will always be pointing upwards like that, so your projectile motion will simply be straight up and straight down. It's less interesting, but it certainly is easier to calculate. So for any point, the range will always be 0, and we'll just be looking at the height and the time, and obviously velocities and accelerations as well. In your booklets at the bottom of page 48 are 7 points to note about projectile motion. Now, these are very important, not just for a conceptual understanding, but they will also help you to solve equations and will give you shortcuts and help you particularly with the shorter questions. I could just read through this, but you can do that. And I want you to keep your booklets open, refer to these 7 notes, and I'm going to use the projectile motion simulation from PHET, and we're going to investigate these 7 points. So let's consider the first of the 7 points to note at the bottom of page 48. First point says you need to start by deciding which motion will be positive. I would strongly suggest that in all these questions, you decide that upward motion will be positive and you keep it that way. It is acceptable and it will be marked correct to have downward motion positive, but it's much simpler to say that while something is going up, it's positive motion, positive velocity. While it is coming down, it is negative motion and negative velocity. That will simply make your life much simpler. The second point is quite surprising. It says that the acceleration will be the same in magnitude and direction at any point in the object's flight. Now we can switch on an acceleration vector and you'll see a yellow arrow. And as I shoot that object, you'll see that no matter where it is, the acceleration vector is exactly the same. It's always pointing downwards. It's a negative acceleration because it's caused by the force of gravity, which is down towards the center of the Earth. Now, although you're not required to do two-dimensional projectile motion, it's sometimes easier to see what happens by shooting it at an angle. And you'll see here, no matter where the ball is, the acceleration vector is always pointing vertically downward. It's the only force which is experienced because we've set the air friction to be 0. Point number 3, let's turn off the acceleration vector and look at a velocity vector. And again, let's point it straight upwards as we should for school. Now have a look at the green velocity vector, and you'll see that it starts off positive, goes through 0, and then negative. Let's slow that down a bit. So as the projectile emerges from the cannon, it has a high positive upward velocity. The velocity gets less and less and less. At the highest point Here the velocity is 0, and that's important to note. That's point number 4. And then the acceleration downwards causes the velocity to change direction and to increase in a negative direction until the object lands. Let's just look at that one more time. Positive at the highest point, point number 4, velocity is 0, and then it changes to negative for the downward journey. Point number 5 says that displacement will be positive above the starting point and negative below the starting point. Now, of course, we can do that with PHET by raising this cannon. And we can say if we shoot an object through the air here, this will be positive displacement as long as it's above that starting point of 7 meters. Still positive, and as soon as it drops below, it now has a negative displacement. So the displacement at this end point would be minus 7 meters because it's 7 meters below the point where it started. Of course, this is exactly the same for one-dimensional projectile motion. Displacement is positive as long as it's above the starting point, and as it returns and starts to go below the starting point, so from now, the displacement is negative, and it ends up as minus 7 meters. Point number 5 says that an object thrown upwards takes the same amount of time going up as it does going down. Now we can see that with vertical projectile motion, and we can take our measuring device and measure at the top. The time is 1.53 seconds, and at the end, 3.06 seconds, exactly double. Perhaps this would be easier to see if we just shot it at an angle, shoot it through the air. Then let's go to the highest point. The time is 1.08 seconds, and at the end, time is 2.16. So it took 1.08 seconds from the bottom to the top, and exactly the same time from the top to the bottom. Another 1.08 seconds, or a total of 2.16. This is very important to remember and will help you with a lot of calculations. Finally, point number 7 tells us that any object traveling only under the influence of gravity is in free fall. So if we shoot an object directly up and down, it is in free fall. If we raise our cannon here and we shoot an object at an angle, it is also in free fall. If we shoot an object horizontally, it is in free fall. And even if we shoot a point downwards, it is in free fall. So in all these cases, because the only force acting on the object once it has left the cannon is gravity, we regard it as being in free fall. And remember, in the absence of air friction, it doesn't matter how heavy an object is, it will fall with an acceleration of minus 9.8 meters per second squared. And just to finish with one point I neglected to say from point number 6. Point 6 told us that when you shoot something up, it takes the same time to go up and to go down. It also returns to the ground with the same velocity that it started, but in an opposite direction. That's why now that we're shooting a piano, you can see if we do it slowly, it leaves at 15 meters per second. Velocity becomes 0 at the highest point, changes to negative, and when it lands, it's at minus 15 meters per second, which is why the piano is so easily destroyed. So that's why it's not a good idea to shoot bullets up in the air, because when they come down again, they have the same speed as what they left the rifle with. Once again, takes off at 15 meters per second. And when it lands far away, the landing velocity is also 15 meters per second, but in a different direction. So before we leave the PHET simulation, one last exercise for you to do. This is actually taken from video number 5 on free body diagrams, but I think it'll help you if we repeat it here. So here is an object, let's say it's a cannonball flying through the air, and we want to focus on 3 positions. Position 1 on its way up, position 2 at the top of its rise, and position 3 on the way down. Now, the question is, which of the free body diagrams from A to F is correct at each position 1 to 3? So these are free body diagrams of the forces experienced by the cannonball at each of those positions. Now we've set air resistance to 0, so don't worry about friction, And I want you to think about which is the correct free body diagram for the forces experienced by the ball at position 1, position 2, and position 3. Why don't you pause the video here for 3 minutes and discuss this in groups and try to choose one letter for each of these. The letters can be repeated, but see if you can come up with the correct free body diagrams. So I hope you've taken some time to think about it. And in fact, the correct answer is C in all 3 positions. And it's very important to notice that when an object is in projectile motion with no air friction, the only force that acts on it is the force of gravity. That force always acts downwards or towards the center of the Earth. And therefore, the only acceleration is the acceleration of gravity, minus 9.8 meters per second squared. It's negative because we take upward motion as positive. This is point number 2 in your 7 notes at the bottom of page 48, and it's very important. Well, I hope that last section has given you a better conceptual understanding of projectile motion. But please remember, the idea of these videos is not to try to cover all the content, but rather to sharpen your skills. So let's move on to the mathematical side, the equations for projectile motion. So as we said, anything that flies through the air is a projectile, and it can be very accurately described by equations. Now, if you turn to page 37 in your books, we introduced this progress method for problem solving. You don't have to use it every time, and I encourage you to use it particularly for the 6 to 8 mark questions. Don't waste your time with the 2 or 3 mark questions, but this can be especially helpful in projectile motion. So first of all, P stands for picture. Draw a picture if it helps. Quite often that picture is given on the exam paper. Don't redraw it, just add to it. Secondly, check carefully what is required. Sometimes it's not quite obvious. They might say how long when they want a time, or how far when they want a distance. Oh, obvious, look out for the obvious. Usually that will be either the initial or final velocity is 0, and of course the acceleration of gravity minus 9.8 meters per second squared, if you choose upwards as positive, which I strongly encourage you to do. G, check carefully what has been given. Look at the information you're given. And then R, relate what is given to what is required by E, choosing the correct equation. Now, choosing the correct equation is probably the hardest part of these questions, but don't worry, we'll spend a lot of time helping you to do that. Once you have the correct equation, it's simply a matter of substituting and solving, which I'm sure that you can do. Now, where do we go to our equations? We go to our data sheets. These are on page 38 and 39 in your books, so you should turn there. And we're going to look at the equations of motion, the 4 equations of motion, which you learned in grade 10. Now, they're under a section called motion, and they're the very first equations that you will come across. Of course, one of the problems that people often have is if there are 4 equations of motion, which one am I actually going to choose? By the way, don't get confused by x and y. They really mean the same thing. X is just position, delta x is distance. And when it's in a vertical direction, like for projectile motion, quite often y is used. So let's focus on the variables, which you'll find in projectile motion. We're now on page 48 in your booklets. And that page tells you that there are 5 variables and 1 constant which come up in these equations. Now, these are very familiar to us now. X is position in meters. Quite often we use y for vertical motions. Delta t is the time in seconds. A is the acceleration in meters per second every second. And there's a special acceleration at the bottom, the constant g, the acceleration due to gravity, which is 9.8 meters per second squared. Remember, it'll often be negative because you've chosen upward motion as positive. And then your 2 velocities, initial velocity and final velocity, both in meters per second. So let's go back to our equations in our data sheet on page 38. So we have these 4 equations of motion, and there are 5 variables. Now, the way to choose an equation is often not by what is in the equation, but rather by what is not in the equation. Let me explain what I mean. If you look at the first equation, final velocity equals initial velocity plus a delta t, you'll notice that there is no delta x. There's no mention of position or distance there. So if you have a question which gives you no information about delta x, but you have the other four variables, then that's going to be your equation. If you look at the second equation, I wonder if you can see which of the five variables is missing from the equation. And of course, it's delta t. There's no time dependence in that second equation. So if you know nothing about time, that's your equation of choice. Third equation on the top right, if you look at it, you will see that there's no final velocity. There's always initial velocity in every equation. It's an important initial condition, but this third equation has no final velocity. If you don't know that, this can be a good equation to use. And finally, the last equation does not contain acceleration. So we can actually put these in a table, and you'll find this table on page 48 in your booklets. And we're combining the data sheet from page 38 and this table you find on page 48. There are the four equations of motion. There are the five variables, and we've put ticks or crosses depending on whether that variable is found in the equation of motion or not. So this is the table on page 48. Now, of course, you won't have the table in your exams, but you will have these four equations on your data sheets. And as you'll see, we're going to do four different exam questions. And you'll see a very good way to choose your equation and to solve the problem correctly is to take your initial conditions, fill them in the second row of the table I've highlighted in yellow under the appropriate variable, and then use that to decide which is the correct equation to use. This will make a lot more sense when we look at an exam example. Right, so let's bring all this theory down to earth by looking at an illustrative exam example. Now, this is question 3 from the KwaZulu-Natal September 2020 preparatory exam. It's not in your booklet, so just pay attention on the screen. Now, you can see by comparison with November 2018 and November 2019, there was a very similar theme. A ball was thrown upwards from a certain height above the ground, a ball thrown upwards from 40 meters above the ground, and a ball thrown upwards from 50 meters above the ground. Ball rises to a certain height and then falls past the initial point. Now, this is a favorite with examiners, and it would do you well to pay attention to this. So here's the question. Ball is thrown vertically upwards from the top of a building with an initial velocity of 12 meters per second. The ball leaves the thrower's hand at a point that's 50 meters above the ground. The ball just misses the edge of the roof on its way down and falls to the ground where it bounces. So there are four questions, and I've arranged them in two groups of two, because the first two questions ask you questions about the point of maximum height, and the next two questions ask about a later point after 4 seconds have elapsed. So we have a picture which we're going to add to. I've highlighted in green what is required: a time, a height, a velocity, and a position. We're going to put in blue what is obvious, like the acceleration of gravity, and highlighted in red some of the data which is given. So looking at the first two questions, let's start with our picture and let's add to it. Once again, we remind ourselves that we'll consider the upward direction and upward motion to be positive. Secondly, the initial velocity of 12 meters per second upwards, we indicate there. And the acceleration, which is just g, is minus 9.8 meters per second squared. It's negative because we've chosen the upward direction as positive. Now let's look at these initial conditions. Here's our 5 variables. Again, don't be confused. We're using y for position rather than x because it is vertical. At point A, at the point that the ball was thrown, of course, our position is 0. Initial velocity we were given is 12. Final velocity, we don't really have one yet. Acceleration is minus 9.8, and t equals 0. That's where everything starts. At point B, which is more important to answer these two questions, we don't know what the position is. In fact, that's what 312 is asking for. Initial velocity is 12 upwards. Final velocity is 0 because that's at the top of the rise. And please remember on your points to note at the bottom, that's point number 4, that velocity will be 0 at the highest point. Acceleration minus 9.8. Both of those are obvious facts which are not directly stated. So you need to look out for the obvious. And then what is the time taken from A to B? Well, we don't know. In fact, that's what question 3.1.1 is asking. Let's do these one at a time. So starting with 311, and then we'll get to 312. And you can see how we've filled in our figures at the top of this table of equations, which is going to help us to select the correct equation. 311, let's focus on the time. So we're looking for t. We have those three numbers. We don't know what y is. So we must choose an equation which has ticks for those four. And only the third equation has ticks for those four. 1, 2, and 4 are no good because of what is missing. So that tells us we must choose equation 3. Final velocity equals initial velocity plus acceleration times time. So we fill in that equation there. Then we put in our numbers. Final velocity is just 0. Initial velocity is 12. That was given. Acceleration is minus 9.8 times delta t, which is what we are looking for. That is what is required. Simply solving that for delta t, we get delta t is equal to 1.2245 seconds. So you can see this table method really helps you to choose the correct equation. Now we can take that answer from 311 and we can actually put it into our table for 312 because it's an extra piece of data. Don't worry about using that again, because even if you got that number wrong, you would only be marked down once. They would carry on positive marking with your answer, whatever it is. The second question asks for the maximum height. So we're looking for y. In fact, we're looking for y, and we actually have all the other numbers. So we could actually use any one of these four equations. And if you don't want to carry forward the time, then you would probably use equation 2 and just use these four variables here. But equation 2 has a couple of squares in, which makes it a bit more difficult. So why not use equation 4? There are no squares. It's the simplest equation, and we'll just use the value of time that's been carried forward. So using equation 4, we simply fill in our final velocity was 0, initial velocity 12. Our time carried through from 311 is 1.2245 seconds, and we divide by 2. And when you solve for delta y, we get 7.35. Now remember, the question asks for the maximum height above the ground, and the ball started from a height of 50. So don't forget to add 50 to get the final answer of 57.35 meters above the ground. So 3.1.1 and 3.1.2 deal with point B at the top of the rise. Now we need to start again for 313 and 314 because they deal with point C, where the ball has already gone over the top and is on its way down. We don't know exactly where point C is, but we know that it happens after 4 seconds. Now 313 asks for the velocity, which will be the final velocity. 314 asks for the position, which is y. We can now fill in the time of 4 seconds, which is given. Initial velocity is still 12. Acceleration is still minus 9.8. Once again, these figures will help us to choose the correct equation. Let's do it one at a time. 313 asks for the velocity of the ball at t equals 4 seconds. So we're looking for the final velocity. That's what is required. What is given is initial velocity and time, and what is obvious is acceleration. Once again, because of those four variables that are shaded, we must choose equation 3, which relates those four variables together. So we choose equation 3, final velocity equals initial velocity plus a delta t. Fill in our given values and our obvious values, and we get a final velocity of minus 27.20 meters per second. That confirms the fact that the ball is already on its way down at point C. And finally, what is the position of the ball above the ground at t equals 4? Now we've carried forward that final velocity from 313, and we're looking for y. Once again, because we have all 5 of these variables, we could use any equation. And in fact, you might think of using equation 1 so as not to carry forward that value. That's fine. But again, it has a square in, and equation 4, which is quite legitimate, has no squares. It's the simplest equation. So I would suggest using equation 4. Substitute in your values. Final velocity minus 27.2. Initial velocity 12. Delta t is 4. We divide by 2. And we get delta y is minus 30.4 above the rooftop. But the question says above the ground. So don't forget to add 50 to that. 50 minus 30.4 is 19.6 meters above the ground. So I hope this method helps you with how to progress with these projectile motion problems. We drew a picture. We used the one in the exam, but we added some things to it to remind ourselves. We checked carefully for what is required, and we highlighted that in green and put it into our table. We looked out for what is obvious, for example, the acceleration of gravity, or maybe final velocity equals 0 at the highest point. Then we checked for what is given, which I highlighted in red, and put those into the table. And then once we'd done that, it was quite easy to relate what is required to what is given and to choose the correct equation to use. Please note again, there is more than one way of solving these problems. So make sure that you understand the strategy and don't just try to learn one particular solution. We'll now progress to some actual exam examples from recent papers, and I'd like you to try these before I go through the answers. So now it's your turn to try to use your new skills on 3 exam examples. Once again, I really want to ask you to pause or stop the video here for 32 minutes while you try to complete the questions. Now, these questions don't follow page 48 because we've already looked at them in video 2 on graphs of motion. So you'll find question 3 on pages 14 to 16 in your book. So turn there now. Now, we've already looked at the graph parts of these questions. So for now, I'd like you to answer just the non-graph parts. So on page 14, the 2018 question, please do just 3.1, 3.2, and 3.3. On page 15, the 2019 question, 3.2, 3.3, and 3.4. And on page 16, the 2020 question, 3.2.3 and 3.2.4. Please pause or stop the video here for at least half an hour so that pupils can try these for themselves before going on to the answers. So starting off with the November 2018 question. Talks about a competition where participants must attempt to throw a ball vertically upwards past point T, which is marked on a tall vertical pole. Point T is 3.7 meters above the ground. It may or may not be the highest point during the motion of the ball. Now, one participant throws the ball vertically upwards at a velocity of 7.5 meters per second. That's an important data point. It's going to be our initial velocity from a point that's 1.6 meters above the ground. Now, they've given you a very nice picture, so there's no need to draw one. Ignore the effects of air resistance. So let's quickly deal with 3.1. In which direction is the net force acting on the ball while it moves towards point T? Choose from upwards or downwards and give a reason. Well, the only force acting on the ball is gravity, and that always acts downwards towards the center of the earth. So choose downwards, and the reason for the answer is the force of gravity. This is, of course, point number 2 in your points to note at the bottom of page 48. Then let's take some more time on 3.2 and 3.3. Calculate the time taken, that's what's required, and determine whether the ball will pass point T or not. So here it's not quite obvious what is required, but of course what you must do is calculate the maximum height reached, and then you'll be able to see whether that is more than 3.7 meters or not. And never forget that the ball starts off 1.6 meters above the ground. So let's look at the first part of the question. Calculate the time taken by the ball to reach its highest point, and then 3.3 will ask for the maximum height reached. So once again, we're going to remember that positive motion and positive direction is upwards. We're going to take our table. fill in our initial conditions. We know that VI is 7.5 meters per second up. That was given. Some obvious things, because it's going to the highest point, final velocity is naught. Notice how this keeps coming up, and that's 0.4 on your points to note. Acceleration is minus 9.8 meters per second because it's downwards. Then 3.2 asks for the time, and 3.3 asks for the height itself. Let's do these one at a time. 3.2 is asking for the time taken to reach the highest point. We've shaded the variables we know about or are looking for. And once again, equation 3 comes to our help because it has ticks for all 4 of those variables. So it relates what is required, which is t, to what is given, which is vi, vf, and a. So we choose that equation, fill in the numbers. It's very simple. Final velocity is naught, initial velocity 7.5, gravity minus 9.8. Solve for delta t, and we get delta t is 0.765 seconds. Not too difficult for 3 marks. 3.3 says determine by means of a calculation whether the ball will pass point T or not. Remember, we said what they're basically asking you to do is to calculate the maximum height reached and see if that is greater than 3.7 meters, not forgetting that the ball starts 1.6 meters above the ground. So we've carried forward the answer from the previous question. T is 0.765, and we're free to use that without fear. And we are looking for y in this case. So we now know about all the variables. So again, we can choose any of the equations. But once again, my advice is to use the simplest equation without any squares or anything like that. And in this case, delta y is v final plus v initial times delta t over 2. Put in the values, final velocity 0, initial velocity 7.5, delta t carried forward, divide by 2. We get delta y is 2.87 meters above the starting point. But to get the maximum height, the total height, we must add the 1.6 meters from where it started. That gives us a total of 4.47 meters above the ground. So we can confidently say, yes, the ball would pass point T, which is only 3.7 meters above the ground. Now, the November 2019 question was quite challenging compared with November 2018. Let's have a look at it. Again, a similar situation, a stone thrown vertically upwards from the edge of a roof. And the initial calculations are very simple, but then a second stone is dropped and you're asked to compare the motion of 2 bodies, which makes it quite a lot more difficult. Once again, we're going to regard upward motion and upward direction as positive. Let's quickly deal with 3.3. Write down the magnitude and direction of the acceleration of stone A at this maximum height. Now again, this came up in our points at the bottom of page 48, is wherever you are, the acceleration is always equal to g, the acceleration of gravity, and is always minus 9.8 meters per second squared. 2 easy marks. So let's look at 3.2. Calculate the maximum height above the ground reached by stone A. So we've drawn a picture. And again, the picture given in the exam was fine. We didn't need to redraw it. What is required is the maximum height, or y, that's 3.2. What is obvious is that the final velocity is naught because it's a maximum height. Remember 0.4 in your notes, and that the acceleration is minus 9.8 meters per second squared. So once again, these are the 4 variables we're looking at. We don't know anything at all about time, so we can't use any equation which requires time. The only one that leaves time out is the second one, and that ticks all our boxes. So that tells us to use this equation of motion. Final velocity squared equals initial velocity squared plus 2a delta y. So we can solve that for delta y. And of course, our final velocity is 0. And just changing the subject to the formula, we get delta y equals 10 squared. 10 was the initial velocity, divided by 2 times 9.8. 9.8 is, of course, the acceleration. Because it's been taken to the other side of the equation, it's lost its minus sign. That gives us delta y equals 5.10 meters above the starting point. But the question asked for above the ground. So we must add the 40 meters of the building. And that gives us a height of 45.10 meters above the ground. Now, 3.4 is completely different, and it tells us stone B is dropped from rest from the edge of the roof X seconds after stone A was thrown upwards. They pass each other when they are 29.74 meters above the ground. Now, because that's 40, you can see that's a point already on the way down. Calculate the value of X. Now, this is quite tricky. So what's our strategy going to be? First of all, we're going to note the meeting point when they pass each other is 29.74 meters above the ground, but that means it's 10.26 meters below the starting point, because we're doing everything with reference to that starting point. Secondly, we're going to calculate the time taken for stone A to reach the meeting point. Then separately calculate the time taken for stone B to reach the meeting point. And then simply subtract these to find delta t. So TA minus TB will be equal to X, which is the number of seconds after stone A was thrown that stone B was dropped. Let's look at that another way to help you understand it. As I said, it's not that important for you to see the final answer. There's lots of options. It's really important for you to understand the nature of this question. Now, you'll recall in video 2, we looked at the graph question, which was 3.5. And in fact, this part helps you understand 3.4. So we're going to redraw this with the drawing from the exam and the graph part of it on the right-hand side. So stone A is thrown upwards, and on the graph, that blue trajectory is that of stone A. It starts from 40 meters, goes up to 45.10, we've just calculated, and then falls to 29.74. And that takes a total time from 0 to G seconds. Then we also told about stone B. It is dropped, it's not thrown down, and it's dropped from the same point where A started, and it is in free fall. Now we notice that a time delta t of x seconds elapses between A being thrown and B being dropped. And on the graph, we would see that delta t as the distance from 0 to f seconds. That's what we need to try to find. Then there's a second point where the two balls pass each other. Obviously, A is traveling faster and it catches up and passes B. But at the moment they're together, we're told that that point is 29.74 meters above the ground. So that corresponds to this height C over here, 29.74 meters, where the balls pass each other. Now, more importantly for us, that point is minus 10.26 meters below the starting point, because we're going to do all our calculations with reference to that starting point. So we will calculate TA, the time taken for A to go up to the maximum height, down past the starting point, and 10.26 meters lower. Then we're going to calculate TB, the time taken for B to free fall from the starting point, 10.26 meters lower. And then we'll simply subtract these, and you can see the difference between those will give us X. So let's start with stone A, which had a longer flight. It went all the way up and down again to that point over there. Let's take our table and fill in everything we know. Well, we know that the position that it ended up in was minus 10.26 meters because it's below the starting point. We know the initial velocity was plus 10 meters per second because it was thrown upwards. We don't know the final velocity. We know that acceleration was 9.8, and we're looking for delta TA, the time taken for the stone to go up, around, and down again. Now, once again, using our table, it's very simple to choose an equation. There's only one that ticks all four boxes, and that relates what is required, the time, to the three variables that were given, and that doesn't need final velocity. So we use that equation, we fill in the numbers that we know, very simple. We solve for t, that'll take a little bit more work, which I'll leave to you, but you'll discover that delta TA is 2.79 seconds. Let's look at stone B. For stone B, it simply drops minus 10.26 meters. In this case, the initial velocity is 0 because it starts from rest. Acceleration still minus 9.8, position still minus 10.26, and we're looking for delta TB. Again, because we don't know the final velocity, we must use the same equation. We take the equation. This time it's a little bit easier because initial velocity is 0. So it's a bit easier to solve for delta t, but again, I'll leave you to do the maths. And we get that delta TB is 1.45 seconds. As we expected, it had a shorter travel time. Now we take those two times and we put them next to our graph here. We say delta TA was 2.79 seconds. That was the time to go up to the maximum and all the way down to the meeting point. Delta TB was only 1.45, the time to drop from rest down to the meeting point. Therefore, x, which was the difference between the times, 2.79 minus 1.45, which is equal to 1.34 seconds. Now, I think you'll agree that was quite a lot of work for 6 marks, quite a lot more than in 2018. But I hope you understood the methodology and how one does this very carefully by calculating each time separately and then by calculating the difference between those two times. So our third and final projectile motion example is question 3 from the November 2020 paper. Now, this was entirely based on a graph of a bouncing ball. So I really encourage you, if you haven't done so, to look at video 2 on motion graphs, because being able to analyze these graphs is very important. We won't do 3.1, which is just a recall question. And please note 3.2.1 and 3.2.2 were covered very carefully in video 2 on motion graphs. So we won't go through those again. We're going to focus on 3.2.3 and 3.2.4. Although these involve an analysis of the graph, they're more based on calculations using your equations of motion. What we will do is just take the answer for 3.2.2, and that was 0.62 seconds. That was the time to reach the maximum height after the first bounce, because we might need to use that in the next question. 3.2.3 is only 3 marks. So I'm not going to go through the whole progress method. You've had lots of practice by now, and we will do it in the next question. So just 2 ways to calculate it, although there are more than this. Please note the question says the speed at which the ball leaves the floor at the first bounce. So there's the first bounce. You want to know what speed was required to get it up to that height of 1.8 meters. The one method is to use this equation, final velocity squared equals initial velocity squared plus 2g delta x. Now, of course, point number 4 in your notes at the bottom of page 48, at the top of the rise, final velocity is 0. That is something obvious, but it's not given and is easy to forget. So because VF is 0, we can rearrange this, take VI squared to the other side, and simply put in delta x, the height of 1.8, gravity, and solve for initial velocity. And we get an initial velocity of 5.94 meters per second. Of course, it's positive because it is upwards. Now, another way to solve this using a different equation of motion is final velocity equals initial velocity plus g delta t, carrying forward the value of delta t that we obtained in 3.2.2. So just filling in final velocity is 0. Initial velocity is what we want to calculate. 0.62 is the time that was carried forward, and that'll give us an initial velocity of 6.08 meters per second. Now, using the different methods, particularly with the squares and so on, does give you a slightly different answer, but both of these answers, as they stand, are entirely acceptable in the marking memorandum. So you could use either method. It's just 3 marks. Finally, 3.2.4 asks for the time t indicated on the graph. Now, the way we're going to do this is we're going to calculate the time from A to B. So this will be the last fall from the last maximum height to the final bounce there, just to make some space. So we're focusing on the time, that time from A to B. And then we will simply take 1.97 and add 2 of those time periods to reach point T, remembering the fact that it takes the same time to go up as to go down. So our picture is really just based on the graph. And what we're looking for is the time T on the graph. So that's what's required. And we're going to look initially for delta t AB and then use that to find the actual time. What's obvious, because we're starting from the top of the rise, initial velocity is 0 and acceleration minus 9.8 meters per second squared. Now, please notice our position from A to B is minus 1.2 because it's falling from the starting point. So that's quite important. We don't know what the final velocity will be. So the equation we use is equation 1. It ticks all our boxes. It relates what is required to the 3 items which are given. So from A to B, delta y equals VI delta t plus half A delta t squared. Initial velocity is 0. That's useful. Delta y is minus 1.2. And we fill in gravity and we solve for delta t squared. And that gives us an answer that delta t AB, which is that period of time there, is 0.49 seconds. So now it's quite an easy calculation. T on the graph will be 1.97, that fixed point, plus 2 of those time periods, 0.49. And that gives us a value that T is equal to 2.96 seconds. So I think you can see just how important it is to be able to analyze graphs, to get data off graphs, and to do these calculations. Just for interest, how were marks allocated? This was a 6-mark question. So there was 1 mark for finding the correct equation. And notice that's not the only equation that you can use. There's lots of other options given in the marking memorandum. Then there was 1 mark for substituting in the position of minus 1.2. Another mark for correct substitution on the right-hand side of the equation. And then in calculating the time, 1 mark for getting the 1.97, 1 mark for adding 2 0.49 periods, and 1 mark for the final answer. So I hope this has been useful in helping you to prepare for question 3, which is always a projectile motion question. Please use this video 6.3 along with video 2 on graphs of motion, because together they will help you solve the 2 parts of question 3. So please be well prepared. When it comes to your exams, don't be scared, be prepared. Thank you for watching.